Okay, so we have our phi in, our plane wave going in, phi r, our plane wave reflecting, and phi t, our plane wave transmitting. We've solved for the amplitudes for reflection and transmission. To solve for the probabilities, we need to use our probability current density we derived in a previous video. So the general form looks like this, where psi is the time-dependent wave function. In fact, for all our plane waves, the time-dependent solution takes the following form. That is, it's just the time-independent solution that we've been working with multiplied by a winding complex phase, where all the complex phases take the same form here. They wind at the same rate given by the energy of the particle. And so we get the expression for our probability current density for our time-independent wave functions of this form. That is pretty much the same form, but with phi instead of psi. So let's use this to calculate the probabilities rather than the amplitudes of reflection and transmission in the two regions in another worked example. Okay, so let's look at the probability current densities in the two different regions. So from the board we had that J of x is equal to I h bar over 2m phi d by dx phi star minus phi star d by dx phi. In region 1, or rather it's actually the reflection part we'd like, so we'd like J reflected is equal to, as a function of x, we're going to insert phi reflected into here, and remember phi, so we've got phi in is equal to e to the I k x, phi reflected is e to the minus I k x, and that's multiplied, sorry I missed the prefactor, by r, and phi transmitted is e to the I k prime x multiplied by t. So if we stick phi r into here, we find I h bar over 2m out the front. To write it out in full for the first one, so I have r e to the minus I k x d by dx of phi star, so phi star, let's write it out in full, d by dx of r star e to the plus I k x minus phi star is r star e to the I k x, and it's d by dx of r e to the minus I k x, and this equals I h bar over 2m. The r is constant, so the derivative doesn't change it. So we have, and that's true for both cases, so we're going to have a modulus r squared out the front here. D by dx acting on e to the I kx brings down an I k, so we get I k, and it just leaves e to the I kx still. The e to the I kx cancels with the e to the minus I kx, and so that's all we get. And then we would have a minus here, e to the I kx, d by dx on e to the minus I kx brings down a minus I k. Minus and minus is plus, so actually get a plus I k. And so we find that j r is equal to, that's 2 I k here, 2 cancels with a 2 here, we get minus h bar over m modulus r squared k. If we'd have done the same for phi in, we would just have found that k goes to minus k, as you can see here, and we lose the modulus r squared. So we find that j in is equal to plus h bar over m, and we still get the k here. So let's take a quick look at what we've got here. Sorry, let's move that over slightly so you can see it. Good. So look at J in. We have h bar k over m, but remember h bar k from our de Broglie relation is just p, the momentum. And so this is p over m, but p over m it should just be our velocity. Right, classically, momentum would be mass times velocity, and so we can kind of think of this as the velocity, or related to the velocity of the particle. Remember, it's a probability current density. So it tells us how the probability to find the particle evolves with time, but when we look, we always find the particle in one place. So the probability of reflection, let's call it capital R, is let's say it's defined to be, it really is, this is just a sort of physical way to motivate it, it's the probability current density for the reflected wave divided by the probability current density of the ingoing wave. And so in this case, we get divided by the h bar k over m, and we just get minus r squared, and sorry, it should really be the modulus of this because it's a probability. So we get the modulus of this, and so we get modulus r squared. The minus sign, of course, is coming about because J is a vector quantity, so the ingoing wave has positive velocity, if you like, positive probability current density, so the reflected wave must have a negative one because it's a vector quantity. So you can think of K as being negative in this case. If we do the same thing for phi transmitted, we find that J transmitted is equal to, so it's a right going wave. You can do this explicitly. I'm just going to state the result. So we're going to get a plus h bar over m, but we don't get a k, we get a k prime. And we get a modulus t squared, much like we had a modulus r squared for the other case. And so the probability of transmission, which is defined to be J transmitted over J incident, is equal to divide by h bar k over m, and we get modulus t squared k prime over k. And again, sorry, it's really technically the modulus of this, just in case there's any sign coming in there. Okay? So it's not just modulus t squared. The reason for the k prime over k, you can think of it as the particle having different velocities in the different regions. And so you're, say, more likely to find a particle if it's moving slowly in a region, is one loose way to think of what's going on here. So we have the probability for reflection and transmission. And in fact, we can substitute back in the energy E and V naught into this expression if we want to get it back in terms of the energy of the particle and V naught. Okay, so let's take a look now at the case that E is less than V naught, and we'll just switch back to the board for a second.